Good morning, I am Sheetal from BSc Chemistry Honors second year. Today I am going to make an audio recording for visually impaired student. The chapter name is Amines. Introduction. Amines are very important class of nitrogenous compound which may be regarded as derivative of ammonia in which one or more hydrogen atom have been replaced by alkyl or aryl group. For example, methylamine, dimethylamine, trimethylamine. The number of hydrogen atoms that have been replaced serve as the basis of classification of amine as described below. Classification of amines. Amines are classified as primary, secondary, or tertiary amine according to as 1, 2, or 3 hydrogen atom of ammonia molecule have been replaced by alkyl or aryl group as described below. Primary amine. These are the derivative of ammonia in which one hydrogen atom of ammonia have been replaced by alkyl or aryl group. Therefore, they are characterized by the presence of amino group NH2 linked to alkyl or aryl group R. If R is alkyl, the amine is aliphatic amine. If R is aryl amino group is attached to the aromatic ring, the amine is known as aromatic or aryl amine. Amines in which the amino group is attached to the aromatic substituted alkyl group may be called as aryl alkyl amine. However, they are quite similar to aliphatic amine, for example. Secondary amine. These are derived of ammonia in which two hydrogen atom of ammonia have been replaced by alkyl or aryl group. Therefore, they contain amino group linked to two alkyl or aryl group. If the two alkyl or aryl group attached to the nitrogen are identical, the amine is simple. If the two groups are different, then amine is termed as mixed. Again, the secondary amine may be purely aliphatic or purely aromatic or mixed aliphatic aromatic depending upon the nature of the two groups attached to the nitrogen. Tertiary amine. There are ammonia derivatives in which all the three hydrogen of ammonia have been replaced by alkyl or aryl group. Therefore, they contain tertiary nitrogen attached to three alkyl or aryl group like secondary amine. They may be simple or mixed and purely aliphatic or aromatic or mixed aliphatic aromatic. Beside amines, there is another class of compound called quaternary ammonium compounds or tetraalkyl ammonium compound which are closely related to ammonia. These compounds may be considered to be derivative of ammonium compound in which all the four hydrogen of ammonia and have been replaced by alkyl or aryl group. Structure of amine. The structure of amine and bonding in them is similar to that of ammonia, as in case of ammonia, the nitrogen atom of amine is in the state of sp3 hybridization so that the hybridized orbitals are directed towards the corner of tetrahedron. Thereof, three of these orbitals which contain one electron each from sigma bond with the three group attached to the nitrogen, while the fourth orbital contains a lone pair of electron. For example, the structure of trimethylamine may be depicted as below. Like ammonia, the actual shapes of amine is pyramidal. The C and bond angle are very close to the tetrahedral angle of 109 degree 0.5 degree. The actual angle in trimethylamine being 108 degree. This angle is slightly greater than hydrogen angle of 107 degree in ammonia due to greater steric repulsion between methyl groups as compared to the hydrogen atom in ammonia. Nomenclature of amine. First is aliphatic amines. Aliphatic amines are as named as follows. First is common system. In common system, aliphatic amine are named by adding the word amine to the name of alkyl group or group present in the molecule. For example, methylamine and propylamine, dimethylamine, dimethyl, and butylamine. Second, IUPAC system. In this system, aliphatic primary amines are named by removing the final E of the name of parent alkene and adding the suffix amine. For example, methane amine, propane amine, 3-methyl 1-butane amine. The secondary and tertiary amine are named as nitrogen substituent primary amine, for example, N-methyl methanamine and dimethyl methanamine. If the secondary and tertiary amine are mixed amine, the longest straight chain is taken as belonging to primary amine, for example, N-methyl ethanamine. Ethylamine is the parent amine, the methyl group is the substituent or nitrogen. N-methyl butane 1 amine. Butane 1 amine is the parent amine. Ethyl and methyl are the substituent or nitrogen. N-methyl 3-hexane and dimethyl pentane 3-amine. Sometimes, in case of complex amine or amines having other functional group of higher priority, the compound is named by prefixing the word amino before the name of the parent compound corresponding to the longest possible straight chain. The positions of the various groups along the straight chain are the course given in the accordance with the general IUPAC rules. For example, 2-methyl 1N-methyl aminohexane, 2-amino 3-methyl butanoic acid. Aromatic amines. Aryls amine, the simplest aromatic amine Even though its IUPAC name is benzenamine, it is probably known as aniline. Most of the arylamine amines in which amino group is directly attached to the aromatic ring are generally named as derivative of aniline, although some of them are given special names such as N-methyl aniline or N-methyl benzenamine. Second is N-dimethyl aniline or N-diethyl benzenamine. Third is P-nitroaniline or 4,nitrobenzenamine. Orthotoluidine or 2-methyl aniline or 2-methyl benzenamine. P-anizidine or 4-methoxyaniline or 4-methoxybenzamine. 2,4,6-trimethylaniline or 2,4,6-trimethylbenzamine. Diaryl and triarylamines. They are named in the same way as aliphatic amine, either by writing the name of aryl group followed by the word amine or as nitrogen substituted primary amines. For example, diphenylamine or N-phenylaniline or N-phenylbenzamine, triphenylamine or N-diphenylanilene or N-diphenylbenzamine. Side chain aromatic amines or alkyl are alkyl amines. Amines containing the amino group in the side chain are generally named by either writing the name of alkyl group and adding the word amine or as aryl substituted alkamines, for example, benzylamine or phenylmethanamine, beta-phenyl ethylamine or 2-phenylethanamine. Salts of amine. These are named by replacing the word amine by ammonium and then adding as a separate word the name of the anion, for example, methyl ammonium chloride, diethyl ammonium acetate, and selenium bromide. Preparation of amines. Of the several methods available for the preparation of aliphatic and aromatic amine, the important ones are discussed below. First is reduction of nitro compound. The nitro groups can be easily reduced to an amino group either by catalytic hydrogenation or by certain chemical reduction. This method is very commonly employed for the preparation of primary aromatic amines since aromatic nitro compounds are readily available. In recent years, the method is becoming increasingly important even for preparation aliphatic amines since aliphatic nitro compounds are now being prepared commercially by vapor phase nitrogen of alkane. First is catalytic hydrogenation. It is generally carried out by treating the nitro compound with molecular hydrogenation in the presence of finely divided nickel or platinum. For example, nitrobenzene in the presence of nickel or platinum gives aniline plus H2O. But a serious limitation of catalytic hydrogenation is that other reducible groups such as ethylenic double bond, if present in nitro compound, also get reduced. Second is chemical reduction. Chemical reduction of nitro compound is usually brought about by adding hydrochloric acid to a mixture of nitro compound and a metal such as granulated tin or iron. The amine is obtained in the form of its salt from which the free amines is recovered by the addition of alkali followed by steam distillation. For example, nitrobenzene in the presence of SnHCl gives 2-amine salt. In the presence of OH negative, steam distillation gives aniline. P-nitrotoluene in the presence of iron HCl gives P-toluidine. Lithium aluminium hydroxide can also be employed as a reducing agent in case of aliphatic nitro compound. If the desired to be reduced only one nitro group of the compound containing two or more nitro groups, the selective reduction can be achieved by using ammonium hydrogen sulfate. Second is reduction of nitrile. Aliphatic or an alkyl primary amine can be obtained conventionally by reduction of nitrile. The reduction may be brought out by catalytic hydrogenation or by chemical reducing agent. The chemical reducing agent may be sodium and alcohol, manganese reduction, or lithium aluminium hydroxide. Nitrile themselves can be readily got from alkyl or alkyl halides by reaction with sodium or potassium cyanide. Thus, an alkyl halide can be converted into a primary amine containing an additional carbon atom by first getting the nitrile from the halide and then reducing the nitrile. Third is reduction of oxamines and amide. Reduction of oxamines obtained from aldehyde or ketones by reaction with hydroxylamine and amides gives primary amine in good yield. The reaction may be brought about chemically or catalytically. Fourth is Gabriel thalamide reaction. This is the important method for the preparation of pure aliphatic or alkyl primary amine. Thalamide contain an amino group flanked by two carbonyl groups. so that the hydrogen of imino group is acidic. Therefore, p-phthalamide can be easily converted into the potassium salt by treatment with alcoholic potassium hydroxide. Potassium phthalamide on heating with alkyl or uralkyl halide from N-substituted phthalamide. This is hydrolyzed to yield phthalic acid and the primary amine by heating with 20% hydrochloric acid under pressure or by refluxing with alkali solution. Fifth is Hofmann bromide reaction. When treated with bromine or chlorine in the alkali solution and as amide from an amine containing one carbon atom less than the starting amine. Mechanism. The mechanism of the reaction have been subjected or of much studied as it involves the rearrangement in the structure of the molecule, the hypobromite ion OBr negative generated by the alkaline solution of bromine or hypochlorite ion furnished by the alkaline solution of chlorine initiate the attack on the amide, which is followed by various other steps as summed up below. Step 1 involves the halogenation amide to form an anhaloamide. In step 2, the hydroxide ion abstract the hydrogen ion from anhaloamide. Third step is the anion formed in the second step undergo loss of halide ion to give an unstable species containing an electron deficient nitrogen known as nitrene. The unstable species readily undergo 1 2 shift of alkyne groups to nitrogen yield an isocyanide. It may be noted, however, that step 3, which involves the removal of halide ion, and the step 4, which involves the actual rearrangement of molecule structure, take place simultaneously. Finally, in step 5, the isocyanides get hydrolyzed to form an amine and carbonates. Evidence in the favor of mechanism of the above mechanism is strongly supported by the fact that the intermediate postulated in step first, second, and third can be actually isolated under stable condition. These intermediates yield the expected product of Hofmann degradation on further treatment. It is also to be noted that actual arrangement in step 4 is in keeping with the general pattern of 1-2 shift to electron deficient atom. The migration of group R along with its pair of electron to nitrogen and the transfer of electron pair from nitrogen take place simultaneously. Therefore, this migration should occur with complete retention of configuration. This is found to be actually so by the studies of compound containing chiral carbon. It is to be noted that method first to fifth given above can be used for the preparation of primary amine only. Sixth is reductive amination of aldehyde and ketone. Many aldehyde and ketone changes into primary amine on reaction with hydrogen and ammonium at temperature to about 373 Kelvin and 150 atmosphere pressure and in the presence of catalysts such as nickel. The reaction is known as reductive amination. Mechanism. Reductive amination involves the formation of amine as an intermediate and proceed through the following mechanism. Like ammonia, primary amine can also be react with aldehyde and ketone to yield secondary amine. For example, benzaldehyde in the presence of CH3 and H2 nickel gives methyl benzylamine. Similarly, secondary amine would react with aldehyde or ketone to furnish tertiary amine. It may be noted, however, that possibly the further reaction between the aldehyde or ketone, the amine formed in a particular case, can be largely restricted by the use of suitable proportions of the reactant. Note both aliphatic and aromatic aldehyde or ketone can be subjected to reductive amination. Moreover, reductive amination of ketone gives rise to amines containing secondary alkyl group as the obvious from the example cited above. Separation of primary, secondary, and tertiary amine. As described above, certain method of preparation of amines led to the formation of mixture of primary, secondary, and tertiary amine and quaternary ammonium salt. When a mixture of amine or salt of amine and quaternary ammonium salt is to be separated, it is first distilled with potassium hydroxide. The quaternary ammonium salt, being non-volatile, is left behind while the mixture of amine distills off. Over this mixture is separated by the following method. First is fractional distillation. This method is generally employed on an industrial scale. The mixture of amine is fractionally distilled by employing high efficient fractionating apparatus. Second is Hofmann method. The mixture of the amine is treated with diethyl oxalate with the primary amine forms and substitute oxamide, a solid. The secondary amine form dialkyl oxamic ester, a liquid, and the tertiary amine does not react. Regeneration of amine on distilling the reaction mixture at the tertiary amine distills over first and it is collected as the distillate. The remaining mixture is cooled and filtered when oxamic ester passes as the filtrate and the oxamide is left as the residue. Oxamide and oxamic esters are now separately boiled with the alkali to get back the original amines. Third is Hinsberg method. The mixture of amine is treated with p-toluene toluene sulfonyl chloride, also known as tosyl chloride or Hinsberg reagent. In the early days, benzene sulfonyl chloride was used as Hinsberg reagent in the presence of sodium hydroxide. The primary amine forms monoalkyl sulfonamide, which dissolved in the sodium hydroxide with the formation of sodium salt. The secondary amine formed dialkyl sulfonamide, which is insoluble in alkane. The tertiary amines does not react at all. Regeneration of amine, the alkyl mixture obtainable is extracted with either ether when the unreacted tertiary amine and sulfonamide of secondary amide passes into the ether layer, while the sodium salt of sulfonamide of primary amine remain in the aqueous layer. Chemical properties of amine. The chemical properties of amine closely resembles those of ammonia and are largely determined by the presence of lone pair of electron on the nitrogen atom. The important properties are discussed below. First is basic character. Like ammonia, all of the classes of amine have a lone pair of electron on the nitrogen atom. Since this pair of electron is available for being shared by other atom, which may be electron pair, amines act as a basis. As such, they undergo the following reaction. First is formation of hydroxide. Like ammonia, the water-soluble amines form substituted ammonium hydroxide which ionize to furnish hydroxyl ion. Second is formation of salt. Being basic in nature, amines react with acid to form salt called amine salt. Reaction with nitrous acid. The three classes of amine react differently with nitrous acid, which is generally obtained in situ by the action of mineral acid or sodium nitrate as illustrated below. A primary aromatic amine reacts with nitrous acid in the cold to yield diazonium salt. This reaction is known as diazotization. The aromatic diazonium salts are sufficiently stable in cold aqueous solution to enable them to be used as important intermediate in the many synthesis process. Primary aliphatic amines also react with cold nitrous acid to yield diazonium salt, but aliphatic diazonium salts are unstable even in cold and decompose as soon as they are formed to yield a complex mixture of different products. It is in the obvious from the above reaction with nitrous acid can be used to determine if the amine is a primary, secondary, or tertiary amine, and in some cases if the amine is an aliphatic or aromatic. Carbamide reaction when a primary amine is formed with chloroform and alcoholic potash and alkyl isocyanide is formed which gives a very offensive smell. Since the reaction is not given by secondary and tertiary amine, it is used for distinguish primary amines from the other classes of amine. The reaction is believed to take place as given below. Action of carbon disulfide when boosted with CS2 in the presence of mercury chloride aliphatic primary amine yield isothiocyanate which smells like mustard oil. The reaction is known as Hofmann mustard oil reaction and can be used for the identification of primary amine. On the other hand, when an aromatic primary amine such as aniline is heated with CS2 and solid KOH, it gives an N-diphenylurea which forms phenyl isothiocyanate on treatment with concentrated HCl. Reaction with aldehyde and ketone. Primary amines react with aldehyde and ketone to form imines known as Schiff base or aniles. Schiff base on reduction with gives secondary amine. Secondary amine react with aldehyde and ketone containing alpha hydrogen atom to form carbamines amine, which are highly unstable and readily undergo dehydration to form enamines. Acidic nature. Even though amines are essentially basic in nature, primary and secondary amine can behave as acid, which reacted when reacted with alkaline metals or Grignard reagent. Tertiary amine do not undergo these reactions because they do not contain any alpha hydrogen attached to nitrogen. Oxidation. All classes of amine are readily oxidized, but the nature of the product form depends upon the starting amine and the oxidizing agent employed. The oxidation can be brought about by the variety of oxidizing agents such as H2O2, peroxoacid and Carros acid H2SO5. Primary and secondary aliphatic amine usually give complex mixture on oxidation, but tertiary amine are cleanly oxidized to tetraarylamine oxide. In case of arylamine, the oxidation is not confined to amino group but also take place in the ring. For example, aniline gives benzoquinone. Electrophilic aromatic substitution in arylamine. In addition to chemical property for amino group discussed above, the ring of arylamine can undergo the typical electrophilic aromatic substitution reaction, which involves carbocation as intermediate. In these reactions, the NH2, NHR, and NR2 group act as a strongly activating and ortho-para-directing group. This is because the pair of unshared electron on nitrogen of these groups enables these groups to donate electron by resonance mechanism. During the electrophilic aromatic substitution of benzene itself, the carbocation intermediate formed by attack of electrophilic resonance hybrid of three contributing structure as shown below. But when benzene ring containing NH2 NHR or NR2 group attached to it undergo electrophilic attack, the intermediate carbocation formed can have additional contributing structure. These structures, such as first para position at ortho position, are formed by the resonance interaction of lone pair of electron on nitrogen with benzene ring. It may be seen that these structures are particularly stable since in them every atom except hydrogen, which cannot of course have more than two electrons, have a complete octet of electrons. The formation of additional contributing structure leads to the stabilization of intermediate carbocation and increase its ease of formation. As a result, ring substitution in aromatic amines occurs very rapidly and preferably at ortho and para positions. It may be accompanied by even side reaction. Protection of amino group. It is sometimes necessary to decrease the speed of reactions or prevent the formation of side product by acylation of the amino group before introducing a substituent into the ring. The acylated amino group is also activating an ortho para-directing but much less powerful than the free amino group. This is due to the fact that oxygen of carbonyl group tends to withdraw the unshared pair of electron or nitrogen towards itself and thus make this pair less available for donation to aromatic ring. As such, the ring is not strongly activated, therefore the protection of amino group by acylation can be used to control the rate of electrophilic substitution and prevent the occurrence of side reactions. First is halogenation. Halogenation of aromatic amine proceeds at very faster rate and all the available ortho and para position get halogenated even in the absence of catalyst. Thus, aniline on treatment with aqueous solution of bromine readily forms 2,4-tribromoaniline. If the monohalogenation derivative is desired, the amino group is first acylated and then the rings is halogenated. After the halogenation, the parent amino group is regenerated by hydrolysis of the substituent amide to give the substituted amine. Second is nitration. Direct nitration of aromatic amine is not feasible. It proceeds due to the following reason. First is direct nitration result in the formation of oxidation product in addition to the desired nitro compound. This is because nitric acid is not only nitrating agent but also an oxidizing agent, and highly activated benzene ring can easily get oxidized. Thus, considerable amount of amine would be lost by oxidation. Second, even though amino group is ortho-para-directing, direct nitration result in the formation of mixture of meta and para derivative. It is believed that strongly acidic solution, the amine is converted into anilinium ion. In anilinium ion, the nitrogen has no longer got an unshared pair of electron but has a positive charge, and as such directs a large percentage of entering group to the meta position. In the view of the reasons given above, nitration is being carried out by using the acylated amines rather than the free amine. Acylations lower the reactivity of aromatic ring and this prevent the formation of oxidation product. At the same time, acylated amino group leads to the formation of product having the substituent in ortho and para position only. Third is sulfonation. In spite of the presence of strongly activating amino group, the sulfonation of ammonium amines takes place under rather drastic condition. For instance, aniline gets sulfonated only when heated at 453-463 Kelvin for 4 to 5 hours with concentrated sulfuric acid. Para-aminobenzene sulfonic acid, commonly called sulfanilic acid, being the main product, the process is known as packing and take place via the amine salt anilinium hydrogen sulfate in this case. The use of strong reaction condition can be explained in terms of the fact that amine is first converted into anilinium salt. This salt contains the NH3 positive group, which is electron attacking and therefore has a deactivating influence on the ring. In that cases, however, the main product may be expected to be meta isomer and not para. The predominant formation of para product is justified by pointing out the sulfonation. Unlike other substitution reaction, it is reversible in nature. Accordingly, the formation of the product is determined by the position of equilibrium and not the relative rate of formation of different isomer. It appears that the equilibrium favors the p isomer because it is more stable isomer. It is also quite possible that the sulfonation of amine may involve some mechanism which is entirely different from the other aromatics reaction. Zwitter ion structure. It may be noted that the ammonium sulfonic acid such as sulfanilic acid contain both the acidic and the basic group. Therefore, it would not be unexpected if the group reacted to form an intermolecular salt. The sulfanilic acid exists largely in the form of an internal salt in which the hydrogen ions from the sulfonic acid group has been taken up by the amino group. This type of internal salt is known as dipolar or Zwitter ion. Supporting evidence, the Zwitter ion structure of sulfanilic acid implies the absence of free amino or sulfonilic group in its molecule. This is supported by its properties. Sulfonylic acid decomposes with melting at 553 to 573 Kelvin, while benzene sulfonic acid having the free sulfonic acid group and the aniline having the free amino group melts at only 339 Kelvin and 268 Kelvin respectively. Second is sulfonylic acid is almost insoluble in water as well as most organic solvent. In contrast to this, sulfonic acid are generally highly soluble in water while amines are generally soluble in organic solvent. Third is sulfonylic acid is insoluble in aqueous mineral acid whereas amines go into the solution with the formation of salts. Sulfonylic acid however dissolve in aqueous bases such as NaOH. This is because the strongly basic hydroxide ion can abstract a proton from NH3 positive to form the water soluble sodium salt. Explanation of relative basicities. The basicities of amines depends upon the availability of electron pair on nitrogen atom and the stability of the substituted ammonium ion formed. As such, any factor that can increase the availability of electron pair on nitrogen or increase the stability of ammonium ion relative to the parent amine will increase the basicity of amine. On the other hand, any factor that has the opposite effect will decrease the basicity. First is aliphatic amine. Greater the basicity of aliphatic amine as compared to the ammonia. First is inductive effect. The greater basicity of aliphatic amine as compared to ammonia can be explained in terms of electron releasing inductive effect of alkyl group. Aliphatic amines contain one or more alkyl group in place of hydrogen atom of ammonia. Now an alkyl group being electron releasing increase the electron density on nitrogen and thus make the electron pair on nitrogen more available for sharing. At the same time, the electron releasing inductive effect of alkyl group decrease the positive charge on the substituent ammonia and formed the amines and thus increase its stability. It may be noted that due to the inductive effect alone, a tertiary amine should be more basic than a secondary amine, which in turn is more basic than a primary amine, while secondary amine are invariably found to be stronger bases than primary amine. The tertiary amine have been found to be weaker than secondary amine and sometimes even more weaker than primary amine, in evident from the observed order of the following cases. CH3 twice NH, CH3NH2, CH thrice nitrogen, C2H5 twice NH, C2H5 thrice nitrogen, C2H5 NH2. This means that relative basicities of primary, secondary, and tertiary amines cannot be explained in terms of electronic factor alone. There are other factors, particularly solvation effect, which are also plays their role as explained below. Second is solvation effect. This is another factor which strongly influences the basicity of amine in aqueous solution. The substituent ammonium ion formed by the amine by taking up a proton are highly solvated in water, though hydrogen bonding and are therefore strongly stabilized, but the extent of solvation and constituent stabilization depends upon the number of hydrogen atom in substituted ammonium ion, which can form hydrogen bond as shown below. As such, the basicity of amine should decrease corresponding in the order. It is therefore apparent that the inductive effect and solvation effect has opposing influence on the basicity of aliphatic amine. The least stabilization of ammonium ion obtained from tertiary amine is responsible for lesser basicity of such amine that expected on the basis of inductive effect alone. The fact that triethyl ammonium is stronger base than ethylamine, while trimethylamine is a weaker base than methylamine, can be explained as follows. Ethyl group has a greater electron releasing effect than methylamine. Therefore, in case of ethylamine, the plus I effect of 3-ethyl group is trimethylamine become the dominating factor as compared to hydrogen bonding of ion derived from ethylamine. As a result of trimethylamine is stronger base than the ethylamine, but in case of trimethylamine and methylamine, the greater hydrogen effect bonding of ion derived from primary amine dominates over the plus I effect of 3-methyl group in the trimethylamine. Therefore, methylamine is a stronger base than trimethylamine.